Alright. So here is the first thing I would like us to do, which is, so I'm not going to do this as like a quiz that I'm going to play. It's going to be something that I want you all to do awesome. So I'm going to start with my turn. I'm going to start with you doing. Namely this. So this is an application of the Pythagorean identity. Here's a question. Suppose I tell you that you have some angle which sits in quadrant 2 on this picture. And suppose I tell you that the sine of this angle is the square root of 5 divided by 3. You can get a decimal approximation for root 5 divided by 3, but if you do that, you'll lose lots of information and all of your other answers will have some question. Let's just call in all of the trig functions of this. Cosine, secant, cosecant, tangent, cotangent, in diagonal. The key fact you'll need to do this is the Pythagorean identity, namely sine squared of any angle plus cosine squared of that same angle is always 1. So I saw that using this fact and the things written in this sentence, you can determine cosine of theta. There's one telling you that cosine of this angle. Where you are allowed to talk to each other. So, here's one certain fact. Sine squared plus cosine squared is equal to 1. Does the problem tell you what sine squared or cosine squared is? Yeah, what does the problem tell you? It tells you what sine is. So let's try that color coding, so it's color coded. Sine is root 5 over 3. Let's plug that in. So that means I see root 5 over 3 quantity squared plus, I would like to know what cosine is. That's a current one of this problem. I don't want to have to keep writing cosine, so I'll replace that cosine with c squared equals 1. Does that look like something you could solve for c? And if you solve that for c, you will know what cosine theta is. cosine of theta is? What do people get? Yeah. Anyone settling on a different value?
Negative root 4 over 9.
Yeah.
Well, I took square root 5 squared it. And then since I knew that c like that plus c, since that was the square value, I did 1 minus that, and then put the square root of that, and that around 2/3. I don't know if that's it.
Yeah, so let's compare those two. I found 2 thoughts, which it sounds like you just use a calculator.
Yeah.
Are there any alternate squares underneath that square root? 4 and 9? Yeah, so what's the square root of 4 ninths? 2 thoughts. So your answer is correct. It's not totally simplified. And I'll want that totally simplified for the next step because I'm going to use that. Yeah. Oh yeah, you said negative. So yeah, I lost the negative sign. You know, negative 2 thoughts. Cool. So we have that as the answer. Is there a demand to see for C plus solving this not good? Alright, let's do it. Here's the equation I need to solve it. What seems like a good boss step? So I guess moving this form to the other side has to happen. I think that I'll simplify lost. Right, simplify and solve. What's the square root of what happens when you square that? So this piece becomes 5 ninths. Let's simplify where we can. So this will become 5 over 9 plus c squared equals 1. And then subtract that 5 ninths to the other side. What's 1 minus 5 ninths? 4 ninths. So that gives me c squared equals 4 over 9. How do people feel so far? I want to solve this for c. Am I done solving for c? What's left? Square root both sides to get rid of that square. So, taking the square root of both sides will give me c equals plus or minus the square root of 4 over 9. And I guess there are 2 things you should check for. Whenever you see the square root of something, you should check to see if there are any long squares you can simplify. And there's also a plus or minus there. Whenever you're going for the square root, a plus or minus over here. Should this be plus or minus? Or maybe I should ask you, why minus? Quadrant 2, quadrant 2. This angle's over here. So the x value, which is cosine, will be negative. So it's negative because it is in quadrant 2, and we've already explained the square root of 4 ninths is 2 thirds. Alright, so we have cosine. Cosine is negative 2 over 2. I thought we could use absolutely all of the other functions. Let's do that. One is secant is also, what is secant of theta equals? Okay, negative 3 over 2. Negative 3 over 2. Do I hear any disagreeing answers for what that is? Do I hear any agreeing answers for what that is? Yeah, so let's talk through where that came from. I think that's correct. Where did negative 3 over 2 come from? Where did that answer come from? It's reciprocal of cosine. Secant is 1 over cosine. So secant of theta will be 1 over negative 2 over 3, which is negative 3 over 2. I guess I painted myself into a corner. I don't have space for cotangent. Nope. So you would think that secant would be sine and cosecant would be cosine, but that's not the case. functions and tell you why that is the case. But I can't. I don't know why these things are named the way they're named. But yeah, secant is what I want to say. Cotangent next. I guess it should be secant because it should be the length of some c and it should be the length of some colon on its own. Anyway, cotangent. What is cotangent equal to? I guess maybe just in terms of sine and cosine, what is cotangent? Nope, opposite. Yeah, because we're doing cotangent, I guess it would be reasonable to do tangent cosine. And I know what cosine is. It's negative 2 over 3. And I know what sine is. It is square root 5 over 3. That's an answer. If you wanted like this B answer, you didn't want to simplify it. Just hold one more thumb, you could do that. Plug that into one more thing, you could. But is that always simplified? What's some simplification we could do? You divided the numerator by 3 and divided the denominator by 3. Those will cancel. How many people would sooner just like multiply by the reciprocal? Not long, but you'll do an extra step. This saves that step. And even if you write down the reciprocal, you will see the 3 cancel. So let's see, negative 2 divided by root 5. I claim that this is still not fully simplified. What more should we do? Let's do with that square root. How do you deal with it? Multiply. I think you're dancing around saying that. So in order to turn that root 5 into integer, you want to multiply by root 5, right? But you can't just multiply the denominator by root 5 and you can multiply the numerator by root 5. Is that exactly what both of you were trying to say? Okay, awesome. Multiply and divide by root 5. So that'll be negative 2 root 5, because negative 2 times root 5 is negative 2 times root 5. And what's the denominator now equal to? Yeah, just 5. Neato. So it looks like cotangent of this angle is negative 2 root 5 over 5. Cosecant and tangent, could you determine those by following through a single line of attack? I think since I'm 15 minutes in, I think I'll stop here and not. How many people already computed cosecant or tangent? What do you get for cosecant? You're both correct. This isn't fully simplified. You should get that square root out of the denominator. 3 root 5 over 5. And that's the obvious answer. It should be the reciprocal of sine. What about tangent? What is the tangent of theta equal to? Folks feel pretty good? Cool. So that finishes the topic, the lecture on trigonometry via the units algebra. And we're going to do this trigonometry via another point of view, namely right triangles. So I think I'll start in the middle of the page and tell you the payoff, and then I'll say where the result comes from. So here's the fact. If you have any right triangle, and you know an angle in that right triangle, then you can determine some things about the side lengths of this triangle. I'll label these as adjacent, because that's the side adjacent to the known angle theta, opposite, and hypotenuse. Here are the
the facts that hold. The cosine of this angle recovers adjacent over hypotenuse. Sine of theta recovers opposite over hypotenuse. And tangent of theta recovers opposite over adjacent. And before we explain where they come from, where these facts come from, let's just write down the mnemonic that maybe some of you just already remember. If you want to remember these three equations, one way to do it is just remembering the, say it louder though. And there's no ideas in that, right? Torah is spelled with a T, indicating that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And there are various to varying degrees problematic mnemonics that all for the same thing, but I think there's always, if you remember those three syllables, you can remember these facts. Let's see where these facts come from. Because as a mathematician, one thing that I absolutely hate is facts without explanation. Let's say why these three things are true. And let's do it by starting with unifocal trigonometry. So I'll go up to the top of the page now, which said, well, let's see. Does anyone object to me moving that off the page right now? Okay. Seeing no hands for an objection? Let's build towards that. So let's start with this right triangle. Here is a focal right triangle inside of a unit circle. Inside of a unit circle. So this is a circle of radius 1. Tell me, what is the length of the hypotenuse of that triangle? 1. It's in the unit circle, that's the radius of the unit circle. This hypotenuse is 1. What's the length of the edge opposite? Sine theta. Why sine theta? Oh, sure. That's true, but that's a little bit circular because I'm trying to like that stuff down there is my goal. I don't want to assume it. Sine is the y value though, right? If I'm going on the unit circle, sine is the y value. Well, the height of this triangle is the y value. So because this is the opposite is the y value, you get sine of theta. So this red side length is indeed sine theta. And let's just check. If that blue side length is 1 and the red side length is sine theta, do I get sine of theta is opposite over hypotenuse? If sine of theta over 1 is sine of theta. What about the adjacent? What is it? The x value. So the adjacent side is the x value. And what is the x value? In terms of a trig function. Cosine theta. So let's take this triangle and let's scale it up. I think I'll skip this bit in the middle. Let's suppose I take this right triangle, and that's now not on the page, and I scale up every side length by a factor of h. If I take that triangle and scale up everything by a factor of h, this angle will still be theta. What's the hypotenuse if I scale everything by a factor of h? H times 1 is h. So the hypotenuse is length h. If I take the side length opposite theta and scale it by a factor of h, what's the side length opposite that equal to? Times h. I'm scaling everything up by a factor of h. So this length that used to be sine of theta will now be h times the sine of theta. The adjacent used to be cosine theta. Now it will be h multiplied by cosine theta. neat. So that means that hypotenuse times sine theta is equal to the length opposite. If you solve that for sine of theta, do you get opposite divided by hypotenuse? Nice. H times the cosine of theta is the length adjacent. If you solve that for cosine theta, do you get adjacent divided by hypotenuse? That's why SOHCAHTOA total is true. If you start with unisolvable trigonometry, you just scale everything up by a factor of h, you get right triangles. And that might seem super simple-minded, but that's a really powerful observation because an awful lot of right triangles are naturally in the wild, measure things. And so let's start with one just made-up example. Here is a right triangle. It has base 3, height 4, hypotenuse unknown.
We can use this to figure out all of the different functions of theta. Let's start with the hypotenuse. What's the hypotenuse of this triangle? Sorry, compute the hypotenuse of this right triangle. Okay, what do you get? Figure out 5? Did you do that by computing or just no? Awesome. You did it by computing. Good. The other thing that, if I say the expression 3, 4, 5 right triangle, how many people have bought that string of blocks? Yeah, so if you know that string of blocks, you also just know the answer. You can also compute it. Okay, cool. Hypotenuse is length 5. Should I actually go through the one computing the hypotenuse myself?
Alright. Hypotenuse is length 5.
Alright.
Hypotenuse is length 5.
I calculated that's enough information to compute all the trig functions. Let's compute all the trig functions. What's the cosine of theta equal to? You went 3 over 5.
Gesundheit.
Sine of theta? Yeah. 4 over 5.
It should be opposite divided by hypotenuse. Opposite is 4. Hypotenuse is 5.
Tangent?
4 divided by 3. Very good.
Alright, so this seems pretty mild. This is an angle that I can use always in the paradigm. If you start with this triangle that I also just use always in the paradigm, you can compute the trig functions of this angle using this triangle. Here's something that's more powerful. You can go the other way. If you know an angle and a side of it, you can determine lots of other sides.
And let's do exactly that. Here is an exercise which will seem very applied because we're really going to measure some stuff. I need a volunteer who is comfortable standing, measuring the height of their eye line, and then doing some stuff at the back of the classroom. Do I have a volunteer? All right, come on. There's an added bonus in that there's an extra credit which will also occur if you choose this device, which I will have to use at home. So the first thing I need is the height of your eye line. So stand on against the chalkboard. You might even make a mark for your eye line. Ah, this seems easier than me holding that. So take a measure up too. All right. Let's see how far your eyes are. Okay. 64 inches. All right. So you have eye level 64 inches. I'm now going to have you make some measurements using this empty level. So I'd like you to make this. There's a really hole in this. So if you... Oh yeah, that would be necessary. You look up to like the top of the classroom there. And now there's a knob right here on the other side. Rotate that until there's a bubble that you should see appear between two lines. That's very good. Cool. Now pull that away from your eye. And read off that angle for me. So I'll get 2 degrees. Nice. I will now have you go to the back of the classroom and do that again. Sorry, that was just the demonstrating how to use the tool. So, how may the angle to the top of the classroom from where you are? Sorry, your glasses are out here. You need someone else to read it for you. Oh, okay. $14. So it was 14 degrees to the top of the classroom. What's the measure of the angle to the bottom of the classroom now? So you're going to need both of those to determine this. Degrees to the bottom of the classroom. Nice. All right. Those are the measurements I need. I will look on to your glasses. And as an added motivation, there's an extra credit in which you will use the same device to some more measurements, and now you are skilled at it. Oh, you're more skilled than anyone else in the room. 10 degrees down. Let's determine the height of this classroom using this information. So, I know that your eye line, and this should be the same, whichever end of the classroom you measure from, I'm pretty sure the whole of the classroom is close enough to that. To get that that is 64 inches. And here's the payoff. If we know an angle in a right triangle and a side length, and we know everything about that right triangle, I'm going to label some of these points. A, B, C, D, E, and F. Oh, and that's not degrees, that's inches. Is there a right triangle in this picture that you could use to determine some stuff? Is there a right triangle whose side length and angle you know? Nice. Which triangle do you see? I guess this one maybe? I guess you could also use this one, but that would be more work because not everything's labeled yet. So that means I can determine any of the side lengths of that triangle. Which one seems most useful? Let's think about the things we want. My eventual goal is that tall length. And I already know some of that tall length. I know that much of it. So if I could determine DE, that would make me happy. I know an angle in that triangle, but I don't know any sides. If I could determine that side length, that would make me happy. All right. Does it look like we can determine that side length I just drew a right arrow to? Yeah. Which trig function should we use? Tangent seems useful, right? It has nothing to do with the hypotenuse, and I don't know any hypotenuses. So tangent is the only one that doesn't have a hypotenuse. So let's do that. Apparently the tangent of 10 degrees should be opposite, which is the side length BE. No, that's adjacent. Silly. The opposite, which is 64 inches, divided by adjacent, which is side length BE. I haven't used that notation for a side length before, but I'm using it now. If you draw the names of the two coordinates with absolute value bars around them, conventionally that means that you want the length between those 2 points. That look like you could solve for the side length BE? Yeah. What would you get if you solved for the side length BE? Yeah. You're on degree mode. Okay, that was, I think you're in radian mode based on that. Oh no, actually that seems reasonable. The length of the classroom should be much taller than you are. Okay. But but that's a decimal approximation. Give me the exact value. Okay. That's the number that I'll actually care about. Now give me the decimal approximation. Sorry. All right. And there's nothing like how accurately did I measure that height, how accurately were the angles measured. I don't think I can really trust beyond like the tens of inches case anyway. Nice. So we have that. We now know the side length E. I would like next the side length DE. Is there a right triangle involving DE whose angle and side length I know? Yeah. So let's use SOHCAHTOA again. Which trig function looks useful? Tangent. What equation do you get? Let's see. I see this 14-degree angle here. Tangent of 14 degrees is opposite, that's side length DE, divided by side length BE. And I know side length BE. Is that a better equation I could solve for side length DE? I think so. Doing that, I guess you get side length DE is equal to tangent of 14 degrees times the side length of BE, which is tangent 14 degrees times this, times 64 divided by tangent 10 degrees. And I think this is close enough to being the thing that I'm interested in. So let's get a decimal approximation. Oh, maybe before I do that, are there any questions about what's happened so far? All right. So, getting a decimal approximation, you all have, well, some of you maybe have calculators, some of you might not. Let's compute tangent of 14 degrees times 64 inches. Why would it be 64? Oh, it wouldn't, because BE has the 64 in it. So, ideally, that thing in red is exactly the side length BE. So if you use like the 360-inch decimal approximation for BE, that would be the same-ish up to a rounding error. And the rounding error might turn out to be significant. So this is why I'm going to use the exact value. All right. Times 64 divided by tangent of 10 degrees. All right. Giving me about 90 inches. That agree with other people's computation? Nice. How many people did it using that 360 inches number instead of what I have written in it? Did you get also 90 inches? Okay, so the rounding error wasn't enough that it did screw you up. It could have had you off by up to an inch. So, what's the side length, what's the height of the classroom equal to? Say that or yeah, so the side length DE is equal to the length FE plus the side length, well, the side length DF is the thing that I actually want, is equal to side length FE plus the side length DE. This is the height of the room. And I now know all of these numbers. This is approximately 64 inches. Even that 64 inches is approximate because you saw how carefully I was using that tape measure. Plus plus 90 inches is 154 inches. Right, 6 plus 9 is 15, and 4 plus 0 is 1. How many people use a calculator to do that addition? You probably didn't need to, did you? Nice. All right, so 154 inches. In order to just see, is that reasonable? I can't picture 154 inches. Let's convert that to feet, I guess. Say that more. About 14 feet. Eyeballing it, does that look about right? Yeah, I think so. So, here's the point, a point of three functions. They let you make measures locally of things that you can reasonably measure, and conclude from them facts that you can't directly measure. By making only a measurement of how tall you are and some degrees of you standing somewhere, we measure the height of the classroom, which is something, I guess we did that in the past by like counting signal blocks or whatever. But that's totally different. You can measure a height that you can't measure directly using trigonometry. Do you think that might be useful if you want to do things like determine heights of buildings or mountains or trees or stuff? Extra credit advertising. Go out, walk up to my office and borrow from the not happening level. Go out and make some measurements to determine the height of the building on campus. If you like, you can compare that with some information you might be able to find online. I haven't been able to find any information about heights of buildings online. Come by my office, talk me through your computation. Cool. So, nice. Let's do a similar process again, which won't involve any measuring of angles. Here's a totally made-up example. So, let's suppose that there's a building that, by doing a similar process earlier, you have determined to be precisely 100 meters in height. Let's suppose that someone has put on the top of this building a statue of a horse. You like horse statues, and so you want to determine the height of this horse statue because that's just something that interests you. I don't know how. Anyway, you're not going to climb to the top of this building with a tape measure and measure the horse. You could, but you might fall, and even if you don't, by the time you get back down, you would probably get arrested. So let's try to do this in a way that doesn't do that by measuring some angles. So you go out with one of those avenue levels. You stand an unknown distance away from the building. You don't bother measuring it. You measure the angle to the top of the building to be 45 degrees, and then an extra 5 degrees to the top of the horse. So that fall angle is 40 degrees. I claim you now have enough information to determine I claim that you now have enough information to determine the height of the horse. And for the time you have, I can give you two reasonable approaches. I can keep talking, you can guide me through what to do. Or I can just be quiet for a little bit, you could suss out the height of the horse, and walk with those around you. How many people would like me to keep talking? Alright, I think that's enough. If any people, or other people would rather walk on and on their own, in hushed tones, go ahead and collaborate. So let's get started. This is all about our triangle trigonometry. Our triangle trigonometry is useful if you can find a right triangle where you know an angle and a height. Or in fact, any two facts, really. Do you see a right triangle in that picture where you know a side length and an angle? Yeah. Which triangle are you thinking of? The bottom half of it. This is why sometimes it's useful to label points. A, B, C. Triangle ABC looks useful. So, let's call the base of that triangle x and see if we can determine x. I guess again, which trig function looks useful? Tangent. We don't care about any of the hypotenuses in this problem. I guess if you wanted to know how long a rope you would need if you wanted to Batman style grab and hook to the top of the building, tangent the cosine sine would be useful for that. But we don't want to do that. So let's use tangent. So apparently the tangent of 45 degrees should be opposite divided by adjacent. What's the length of the angle opposite this 45 degrees? $100. I guess if you wanted to convert kilometers, a tenth of a kilometer, that seems silly. What's the length of the base? It's side length AB, which I made up a variable name for, so I'll call it X. You can call it AB if you want. It doesn't matter. I don't think you can solve that for that unknown side length. I think so. I think it's like the exact same cross division that was done in the previous problem. So solving for that, I think I get X equals 100 meters divided by the tangent of 45 degrees. That feel pretty okay? Is that the side length that we actually care about in this problem now? So we could get a decimal approximation if we wanted to. I would advocate against using that decimal method. So I think because I have 60 minutes, I won't prioritize getting that decimal approximation yet. But I now know the side length X. All right, what seems like a useful next thing to do? Is there another right triangle in this picture we could use? Yeah, like the whole thing is a right triangle. So let's use this right triangle next. Now let's follow the same procedure. Tangent of 40 degrees will also be opposite over adjacent. What's the side length opposite? $100 plus force. If you want to make up a different variable name than force, then do it. Plus force. Don't do that on your own. That would be impossible. It's at best a funny gag right now. What's the length of the adjacent? Yeah, it's the thing right now called X. Maybe you can plug in what that's equal to. That would look something you can solve for force. Maybe, well, so I guess step one would be multiply that denominator to the other side. 100 meters plus force is equal to tangent 40 degrees from that, multiplied by 100 meters divided by tangent 45 degrees. So what you need to do if you want to know what force is. Subtract 100 from whatever's on the other side. Force equals tangent 40 degrees times 100 meters divided by tangent 45 degrees minus 100 meters. That now, so that now that I have the thing I'm actually interested in, let's get that decimal approximation. In fact, how many people have already gotten decimal approximation? But yeah. About 19.8 meters. A fairly tall statue is less. Well, I mean, it's not an actual size statue, I guess. How does this procedure feel? So, here's the point. If you, trigonometry lets you determine things that you can't measure locally. You could get to this cost measure directly. Instead, you can make these indirect measurements and make these. Cool. Alright. So, I actually have more time. No. So, let me give you an overview of what's going to happen. This is where the previous section finished, and I'm not actually done with the content. Let me give you a tour of what will happen next. Here are other trig functions that I claim that we can evaluate. Using the philosophy of right triangle trigonometry, we can, and in fact, we will. So in the next 2 pages, we will actually determine sine and cosine of pi over 4, pi over 3, and pi over 6 by drawing some right triangles. I don't think I have enough time to make all other projects.
maybe I will just start a few minutes on this. Yeah. I think I've gone over enough times that I probably owe you like 3 minutes. Have a good day. Oh, so how many people think they might take me up on the extra credit that come by and we'll have this for me? Yeah. Yeah, I mean, I don't know what any of the heights are going on. And like, if like the thing that screws you up is a 2-minute referendum, that's fine. That's like, I won't kind of run too far, but the ability to score and accuracy is cheaper. The point is, you use pretty much.
So you didn't really, like, 60 outside instead of making, like, the front of that.
It is outlined as extra credit 6.5 if you want to read through the guidance. You do.
I do as well. I think it's supposed to be nice. At the very least, there's like a with a little more informed.
What? Why would anyone live here? Why? So I take it then your plans go after graduation involve not being in Wisconsin?
Alright, keep in mind that there are bad things in the South too. Yeah, have you ever appreciated how rarely you see a popular in this song? I did my grad school in Houston.
Mosquitoes. A lot of mosquitoes in fall and summer.
And ticks.
Yeah.
Mosquitoes are fine, ticks are the things that are fine.
Mosquitoes are everywhere though. You can't live with them.
There's not a nice thing.
Are there any other ones?
The only thing that does. Or Iceland. Go off the
Yeah.
Go with the system. No mosquitoes. I think it sounds great. That sounds good.
I mean, yeah, Iceland is not famously known to be a cheap place to live.
I'll make sure I get good Wi-Fi. It doesn't matter. Not even better.
I mean, the ads for travel Iceland, really neat place to visit. Anyway.